بسم الله الرحمن الرحيم. هنبتدي الأول. We just have to start with a few issues that we have to discuss. Basically, we cancel the simulations that were required from you about experiments 6 and 7 because basically I realized that you haven't done any simulations before. The impression I got from the lab engineer was that you already did that in the other experiments, but actually what you did before was just draw the circuit. You didn't simulate the circuit, right?
No, we just draw it and give him signal.
Yes, okay. So basically, given the very tight time frame that we have and the stressful situations that we are all in this term, so basically it doesn't make sense to ask you to learn something new on your own during this time. So basically we canceled that. So right now what's going on in the lab is that the engineer is regrading the lab experiment reports. Basically, whatever you submitted, he's grading the reports right now. And basically, hopefully by the end of this week or maybe next week, sometime next week or something like that, you will get the grades. Well, once I get the grades from the lab engineer, I will post them so that if you have any issues, you can contact the lab engineer. Okay? Basically, some people actually, I think at least two groups actually haven't submitted their lab reports for some reason. So please, if you haven't submitted your lab reports for experiments 1 through 5, please do that as soon as possible. We need the lab reports so that you don't really get delayed or you don't delay the other students, to know their grades. Because actually the lab engineer will grade basically all the reports at the same time. So basically, if it's missing, if the lab reports are missing a few reports, that would be a problem. So basically, they will delay everybody else. So please, if you haven't submitted your reports, your lab reports, please do that as soon as possible. Basically, in this part right there, basically some of you already took the lab or the class project before in another section. So some of you actually had an incomplete or had another EE306 section before, and basically they finished the lab, they finished the project, but actually they didn't pass the previous section. So if you have these grades, if you have the lab grades or the class project grades, please send them to me, and basically I will actually consider them for you instead of having to take them again here in this course. Or some of you actually contacted me, at least 2 of you contacted me regarding this at the beginning of the term, and actually agreed to them. But please remind me so that basically I make sure that I actually post the correct grades for you instead of just basically considering you as absent in both. Okay, so please remind me again about your previous grades in the lab or the class project if you already took them before. We have to schedule 3 exams. I'm really sorry about that, okay? But actually, they are not the same, of course, okay? We need to have like a 10-15 minute lab exam on Blackboard next week, sometime next week. Since we're already done with the experiments, we're not going to do any further experiments. So basically, we're ready to take the lab exam anytime, basically, right now. So please try to arrange a suitable time for you, basically by next time, by Thursday. And if you cannot basically agree on a particular date, or if there are some people who cannot, or you don't have access to them or something like that, then give me what you agreed about, and basically I will post it. And if somebody has a problem, then we can actually accommodate it. Okay? So we just need to schedule the lab exam first. We need to schedule the class project second, and also it's going to be like 10-15 minute basically exam. It's going to be multiple choice questions. It's going to be on Blackboard. They are not going to be that difficult, but actually we have to have them in order for us to complete the grades for these 2 parts. Okay, so you will have your complete lab grades after you take this exam, and you will know your project grade after you finish the project exam. Okay, we need to finish them next week so that the week after we will have the final exam. It's going to be like a 2-hour final exam. I would like to have it the week after next week, like 2 weeks from today or something like that. Because after that, you will have 1 week to finish all your finals for all the other courses. Most of the other courses will schedule their exams during like after that, like after 2 weeks, okay? So basically, I want to have this exam, I want to have the exam for 306 as early as possible to give you a chance to basically space out your exams. You don't want to have all your exams in a few days, okay? I want to have them, spread out basically in 2 weeks. So basically, we hopefully, basically our exam will be the first, and then hopefully the other exams will not be too close together, okay? It's not going to be a difficult exam. It's going to be basically, it's going to have the same kind of problems that you saw in the homeworks. And it's going to be basically, I'm going to send you a list of the topics that you would expect to see in the exam. Okay. Any questions? Any questions? So basically, I'll send you a list of the topics that you should expect to see in the exam. And basically, this is not going to be like a comprehensive list. Basically, I'm going to choose the most important topics from the start of the course till the end. I'm not going to have everything. I'm going to have a subset that is basically representing the most important take-home message from this course. Okay, so basically after we finish everything on Thursday, after we finish the theoretical part on Thursday, I'm gonna prepare this list and send it to you. Okay, if you have any questions about the list, if you have any confusion about the list, we can talk about it next week, inshallah. Okay, my plan is to finish the theoretical part this Thursday, and starting next week, we will have only 2 lectures on Sunday and Tuesday, like we used to do before. And basically, they will be just review. We're not going to take any new material, okay? I'm going to suggest a few videos for you to basically study the new part that I was planning to give you in the course if everything was according to our earlier plan. So that when you actually go through them, they will actually teach you a few interesting parts that you can use in your project or basically expand your electronic information a little bit, at least practical applications. Okay, they are related to things like the amplifiers, like power supplies, like things of that sort in general. Okay. I want to make sure that all of you know the last day to submit an assignment. The last day to submit any assignments will be April 16th, 2020, okay? If you submit any assignments after that, they are not going to be graded, they are not going to be included in your grades, okay? So this is very important. I'm telling you about that because last term, actually this term, maybe a month ago or something like that, like after the start of the term by a month, a student from last section, the last fall, the 306 course that I taught last fall, came and told me that his project grade wasn't graded. He wasn't posted. Basically, he submitted the project like maybe the end of after the final exam, basically. Okay. And basically expected me to know that he submitted that, to grade it, to include the exam, to include it in the coursework grades. I basically, before the final exam, I usually compile the coursework grades for all the assignments and the projects and the lab and everything, and post them to the students, so that if anybody sees any discrepancy, if anybody sees an assignment that he did, but he doesn't see the grade for, he can tell me so that I can correct it, okay? I did that. And basically, nobody complained about anything. And basically, this student came to me a month after the start of the following term to let me know that there was an assignment that wasn't posted, that the grade for an assignment wasn't posted. Okay, this doesn't make sense. Okay, so basically, whenever I send you the grades, whether it is for the coursework grades or the final exam grades, I gave you at least 24 hours after I post the grades to let me know if you have any issues, if you have any problems, okay? After that, please don't expect any changes to happen to your grade, okay? So if you have any problem, you can tell me, and basically I can correct it. I can discuss it with you, and if you have a grade that wasn't posted, I'll do that. But after that, after the 24 hours, I cannot wait because we have a deadline to submit the grades to August, okay? Last thing is about the IC grades, okay? Some students, actually, last term, there were several students, some of them actually didn't attend any lectures, didn't submit any assignments, didn't have any exams, they didn't attend the lab, they didn't do anything, basically. They didn't show up for the course from the start to finish, okay? And they were asking for IC, okay? This is not basically gonna be approved by the department. This is usually not approved by the department, and basically for any student to get an IC grade, I'm asked by the department to justify why this student deserves an IC, okay? I give only one IC grade last term. That was for a student who had like about 40 out of 60 in the coursework grades, and basically didn't attend the final. For some reason, he didn't attend the final, okay? So basically, if he attends the final has 40% of the marks in this course. So if he passes the final exam, he would pass everything. He would pass the whole course. So basically, this is a very special case, and this was justification for a good justification for the IC grade. Other than that, it is not justified. So basically, please don't ask for IC grades, okay? In general, if you have special circumstances, please send to the chairman, send to the consultant of the chairman for undergraduate courses, and basically get their approval before you ask me, okay? Otherwise, it's not going to be approved by the department, okay? So basically, I'm going to review these items again at the end of this lecture so that those of you who weren't there at the beginning of the lecture can hear about them again, okay? You have any questions about any of them?
No.
Doctor.
No, thank you.
Yes,
Hello.
go ahead.
Are we going to have like normal grades as before?
Yes, normal grades,
Or
yes.
like we're
No, normal grades, not pass fail, no, normal grade.
okay.
Okay, don't worry about the exams. They are not going to have any difficulty. The midterm exam will be basically, you will have bonus marks in the midterm exam, but actually I like to see the coursework grades, the whole coursework grades first, before I actually amend the grades in the midterm exam. So from my experience, it's probably going to be like, you're going to get like 10 plus grades in your midterm exam, okay, at least, okay? But I'll wait until I see the coursework grades first before I actually decide how many points are going to be added to all of you, okay? It's going to be around 10 points, but actually it's not a confirmation that it's going to be like 10 points. It depends on actually how the grades will look like after I see all parts of the coursework grades. Okay, so basically before the end of before the final exam, hopefully, I will post all your grades for all parts of the exam, for all parts of the course so far, and basically everything except for the final. Okay, so that you know exactly how much you got from the 60% that you have for the coursework grade. Okay, before you take the final. Okay, after the final, I will give you the whole thing, give you everything like the final exam grade and the coursework grade and the total course grade. And if you have any issues, please contact me. Okay. So all you have to do now is basically try to schedule the event that I asked you about, like the 15-minute lab exam, the 15-minute class project exam, and the final exam, so that you can actually place it in a time or in a day that you don't have any problems with the other courses. You don't have any conflicts, you don't have any issues. I can have it at night if you want. I can have it early in the morning if you want. It depends on what you want. But I would suggest, given that we have the curfew now, starting from 3 p.m., I would suggest to have the exam after the curfew, because actually during the day you probably have chores, you have things to do, or you have to go buy stuff or something like that, or try maybe do some things basically while you can actually move around. So basically we can have it after 3 p.m. It's not going to be a problem, but please agree on a suitable time for you and a suitable day, of course. Okay? Any questions?
Doctor,
Yes.
should we like select a date between us and then send it to you through email, or like each one sends date?
What do you mean? I mean, you just agree and let me know, basically. Let me know by any means, basically.
Okay.
Did that answer your questions, or?
Yes. Okay, I got it.
Okay. Okay, so let's go back to the where we stopped last time, where we left last time. Basically, the part about the sensor response time. Okay. Basically, when we talk about response time, basically, if you have a transducer, if you have a sensor or a transducer, you're basically converting a physical quantity eventually to an electrical quantity. And such things can happen like mechanically. It can happen through heat diffusion. It can happen like by adding or making some electrons more available, some things of that sort. And such things actually rely on such processes as diffusion, for example. And diffusion is usually very slow. Also, it's not just very slow. Sometimes the processes themselves can act in different ways. Okay, the dynamics of each process can be different from another. Okay, let me give you an example. Okay, let me give you examples just to show what these things mean. Basically, the usual one, if you have a very simple transducer, basically have something that would look like whenever the events, if the events comes here, the initial level of the transducer or the output of the transducer was there. Basically, what happens is that its value is going to change to reach a particular value that corresponds to this stimulus. So basically, this is a stimulus. This is a stimulus. Basically, this is what you call the measure ends. The thing that you have to measure, the thing that you're measuring. Okay, so basically, if this is the level that corresponds to this signal or this value of the thing that you're trying to measure, basically it goes usually very slowly like this. This particular curve reaches a steady state after a certain time, okay? But actually the slope here may vary. And basically this is like a transient time, okay? And depends on the transient time and depends on the kind of measurement sensor that you're using. This transient time can be short, can be long. It might not actually look like this, might look actually a little bit like, for example, sometimes it looks like this, moves a little bit, it overshoots and then goes back like this and eventually goes to the steady state value, okay? An example of something like this, if you stand on a scale, a bathroom scale, basically you have, this is a 0, for example, and this is probably your weight, okay? Basically, when you stand on the sensor, basically the pointer will go to here, but actually it doesn't go to there. It's not gonna go slowly to there and stop there. Basically, it's gonna go like this, and then go back like this, and this, and this, and until it basically settles in the middle here, okay? This actually happens in the moving coil also, by the way. The moving coil, actually, when you're trying to measure a current, this is what happens usually. It basically oscillates a little bit before it settles at the right value of the measure end, and basically stops there. Basically settles there. Okay, this kind of response is called. Basically, this is underdamped and this is overdamped. This is underdamped. This is basically a part of a control algorithm that basically, or basically it depends on the characteristics of the sensor itself. And basically you model it as a control system, and you might end up with something that looks like this, or something that looks like this. Usually the advantage of the overdamped is that you don't have any oscillations, okay? And the advantage of the underdamped is that basically you get around the right value very quickly. So basically, if this is the correct value, you basically reach here in a much shorter time. You reach this point, for example, in a much shorter time than when you reach here. So basically, this takes a long time. And this basically takes a very, very short time, but basically it oscillates around the right value. But basically the oscillation, because you see the oscillations and you see they are around a certain value, you can certainly know where you are, okay? Basically there are advantages for this and advantage for this, but actually the best response is basically when you have basically something in the middle between these two, what they call a critically damped response. Critically damped response is something that goes like this and moves like this. Basically, it's the fastest possible overdamped, or the smallest possible oscillations in the underdamped. Okay, let me show it to you in the lecture.
Doctor?
Yes.
Can we say that the critical damp is like our optimal response
yes,
damp?
this is the optimal response. Yes. So basically, see here, the overdamped takes a long time to settle here. Okay. The underdamped will go very quickly. Actually, it reaches here very quickly, but actually it overshoots. Overshoots meaning that it goes past the right value and then goes back again below the desired value or the correct value, and basically keeps oscillating. They basically usually end up in the steady state at the same time, but sometimes it's not really a good thing to have oscillation. Sometimes you actually don't have the luxury of having underdamped response. Basically, sometimes you cannot overshoot, okay? And basically, it depends on the sensor itself. Depends on the characteristics of the sensor itself. The critically damped basically is something between these two. It's the fastest possible overdamped response. So basically goes from the start all the way to the desired value. It doesn't oscillate around it. So basically it has the advantages of the underdamped in that it's fast. It has a fast response. And basically it has the overdamped advantage that you don't overshoot or undershoot your response. Overshoot, you go up. Undershoot, you go down. Okay? So basically it's very important to have something like this. But sometimes it's very critical, or it's very tricky actually to try to design a critically damped system. Basically, if you take the control systems course, you will know that there are several things that you have to take care of, and basically you have to model your system very well in order for you to be able to design the response in order to become a critically damped system. Okay? We have a few definitions actually. Basically, if you go from here to there, okay. If you go from here to there, okay, basically the response time is defined as the time you take from 10% to 90%. If you basically started from 0 and going all the way up to 100%, 100% representing the correct value that you should actually be at. The time when you go from 10% of the response to 90% is called the response time. Response time, basically, if you look at an amplifier, for example, amplifiers have a response time. And basically, sometimes if you remember what we said before about the slew rate actually is very close to the response time. Okay, basically the slew rate is basically the slope of this line right there. So if the slew rate is high, then you can have a curve that goes like this, much faster. If it's slow, basically you go a little bit further like this, the slope will be like this. Okay, the response time is basically what determines how fast you can get your reading after the quantity that you're trying to measure changes. Okay, so for example, if I tell you that the response time is 1 second, okay, and basically you're trying to measure, for example, if you're trying to measure maybe the temperature of a human being, okay? Would that be okay? Would that be good or bad? 1 second response time, meaning that if the person temperature changes, okay, you will need 1 second in order for you to notice that. Do you think
It's
1
good.
second will be sufficient or will be a good quantity?
Yes.
Actually, it is, right? Because actually the temperature of a human being doesn't change several times every second. Actually, it changes every minute, probably, right? So if you follow it, basically with a sensor having a response time of 1 second, this would be very good. But if you try to measure the temperature of, for example, a car, okay, the temperature of the motor in a car, okay, and basically you know that the temperature is really very high, and basically if you have, if the car loses oil or something like that, its temperature can shoot up much faster than anything that you have in human beings, okay? So basically, if you have a response time of 1 second, it means that the car might be, instead of having the number temperature like 120, something like that, it depends on the car, basically, if you leave it for 1 second, it can raise up to like 200, something like that, it can basically burn the whole motor, okay? So basically, if you have a sensor with a response time of 1 second, this might not be suitable for a control situation or a measurement situation where the measurand changes very quickly, okay? Another example, if you're trying to measure the speed of a car, okay? The speed of a car like Sahir, something like that, okay? If you're trying to measure with Sahir, and basically Sahir needs 1 second, or basically if it needs, for example, 10 seconds, okay, to get the measurement of the speed of the car, okay? This means that if you're driving fast enough, okay, you can actually go past the Sahir sensor, the Sahir detection, okay, without actually allowing Sahir to get the actual speed. Basically, it's not going to be able to get the speed in less than 10 seconds. So if you move fast enough, if you basically go out of sight in 1 second, for example, if you're basically driving at 150, something like that, then you'll not be able to get, basically, it's not going to be able to get your speed, which is basically going to be bad. So basically, in things like Sahir, for example, they use, instead of using ultrasound to get the speed, actually they use microwave or use electromagnetic wave, because they actually can get much faster results, much faster sensing of the speed than ultrasound. Ultrasound cannot do that. Okay, we're going to talk about them in some of the sensors that we're going to talk about later. Okay, so basically the response time depends on the application. So basically there is no such thing as, if you have a response time of 1 second, this would be good. Okay, no. Actually, it depends on the application. 1 second can be very good for one application, can be very bad for another. Okay, so basically it depends on your application. One very important thing is that basically we talked about the response time, is that basically it's the time going from 10% to 90%. How about if the temperature was basically changes from 30 degrees to 40 degrees, okay? And then it goes back from 40 to 30, okay? Actually, this is called, basically gonna have to, the response of the sensor will have to go from the value for 40 degrees into the value for 30 degrees. The curve going up is called the response time. The curve going down is called the recovery time, okay? And they are equal, okay? Let me draw it for you so that you can understand it a little bit better. Basically, assume that you're going from this level to this level, okay? So basically, you're gonna move like this, okay? To reach here, okay? You're gonna stay here for a while and then you're gonna go back, okay? If you look at this here, this is the response time. If you look at this, this is the recovery time. This is response time. This is recovery time. Recovery. Meaning that you're recovering from that increase back to your initial position, okay? So basically, if you have a stimulus that actually required your sensor to go up like this, go up to this level, when the stimulus is over, basically it has to go down like this. And basically, the recovery time is usually exactly the same as the response time. So basically, for some people, they actually wonder, because actually, if you look at the data sheet of a sensor, you will see a response time, but you don't see a recovery time. They are equal. So basically, don't ask about the recovery time because they are the same basically. There is no reason for them to be basically different, because the processes that happen to produce the response basically are reversed when the recovery happens. And they have almost the same magnitude, or at least the same exact range of response times. Actually, it's going to be the same for both. So basically, the response time is equal to the recovery time. And both of them represent the time the sensor needs to change from one value to another. And the response time, it changes from the initial value to the final value. For the recovery time, it basically goes back from the final value to the initial value. Okay? Any questions? Okay. Another property or another classification for a sensor is basically based on the sensor drift. Drift is defined as the gradual change in the measurement output seen while the measurand actually remains constant. So basically, for the same exact quantity that you're trying to measure, basically the outcome of the sensor might change with time, gradually, okay? And this change actually can change. Basically, we talked about the sensitivity, which is the slope between the input and the output. And the offset is basically the value of the output of the sensor when the input is 0. So basically, sometimes you might have sensor drift or gradual change in the output of the sensor itself. Basically, the change will be to the sensitivity. So instead of having the right curve, it can go up or down. And the offset can go also up or down, okay, depending on the technology of the sensor. But in both cases, you will end up with undesired systematic error. Systematic error meaning what? You remember systematic error. Basically, it's an error that is related to the method of measurement. If you're using a particular sensor for your measurement, you're basically considering the sensor as a system used to do the measurement. So basically, when the drift, when sensor drift happens, you will end up with errors, because actually you're doing the same exact experiment at different time with a different outcome. And basically, when sensor drift happens, it means that there will be a new error related to the sensor drift, to the new values or the new response of the sensor. Okay, so when you're taking the measurement later, or a different time, like after a year or something like that, you might end up with a different result because of the sensor drift. Usually in the data sheet of the sensor, sometimes if the sensor drift is critical, or it's, for example, low enough, like it can be of concern to the application, sometimes they actually mention how much the sensor will drift over time, okay? So this is really important. If you're trying to get, sometimes actually they do, if you use a particular sensor, sometimes for medical devices, for example, you have to recalibrate the system every like a year or something like that in order for you to make sure that you take into account such sensor drifts. So basically they will come every year and basically look at the sensor response and basically measure the drift and compensate for it so that you don't get any errors at the output, okay? So basically this sensor drift would require, if it's present and if it's significant, it might require calibration every certain amount of time in order for you to keep the system accurate and basically precise. Okay, so basically what we need to know about the sensor drift is that it's a gradual change in the sensor characteristics, and it's mainly, these changes are mainly to the sensitivity of the sensor or the offset of the sensor. So basically the sensitivity can change by itself, the offset can change by itself, both of them can change together, okay? It depends on the type of the sensor, the technology of the sensor. Just to illustrate an example here, sometimes for a pressure sensor, basically if you're talking about the offset basically starts as 0, and if this time is in years, it might actually go down like this. So basically, you would need to have basically to measure the deviation from the true value and basically compensate for it in order for you to get the correct result. If you don't do that, this would be a problem. An example of that, if you have a bathroom scale, the ميزان الحمام اللي بنستعمله، ميزان اللي هو بتاع القياس، هتلاقي you will find that you have a calibration actually. Before you stand to get your weight, you actually calibrate it to 0, right? Right? Usually it has an adjustment for 0 adjustment. This adjustment is intended to do exactly that. Okay, so when you adjust it to 0, you're actually basically the measurement of the scale. Okay, will basically, if you're not standing on the scale, this will mean the offset of the scale basically. So basically, when you compensate for it, you actually compensate for the sensor drift. And every time if you do that, you make sure that the measurement you're getting is actually accurate. If the sensor offset was, if the scale offset was like 1 kilogram, then and you basically don't correct for it, it means that when you measure your weight, you're basically measuring the weight plus 1. Okay, it's going to be basically, it has an error due to the initial offset of the scale. Okay, so this is very common, and basically the solution to compensate for the sensor drift are actually very common and very easy, and basically have been around for a while. Have any questions? Okay. Another very interesting characteristics of some sensors, not all sensors, some sensors, they might have a sensor hysteresis. This is unusual, might not be a very common, but actually in some sensors, you actually expect to see something like that. And for example, some of the chemical sensors will actually follow such hysteresis, basically. For the usual sensors, if you have a resistance that measures the temperature, for example, as we will see, you don't expect to see a hysteresis, but if you have a chemical sensor, you expect to see that. Sometimes in some mechanical sensors, you expect to see that as well. But actually, you just be aware that there might be a hysteresis. Hysteresis meaning that if you have a certain measurement here, that certain measurement will actually map to a certain value here differently if you're actually moving up or down. Meaning that if you're trying to measure X, the value X, basically the input was X, okay? If basically your measurement of X during if the values were reducing, basically if the previous X was here and this X here is next and the next is here. So if you're going on the going down curve, okay, if you're on the down curve, basically you will get a reading here, Y2. If you are in the up curve, if you are moving on the upper curve here, then you will get an output of Y1. So the output will be different for the same exact input, depending on whether you're going up or going down. Okay, this is unusual, but actually it happens because of some processes in some of the sensors are not reversible, not exactly reversible, meaning that they would require energy, between going up and going down. And basically, this would actually have to be really dealt with in software or something like that. You have to actually have the readings go into a digital side, like a microprocessor, microcontroller, and then determine whether you're going up or going down. And based on that, you actually basically interpret the output as a result. Okay, so this is really important. Okay, if the sensor has a hysteresis, you have to actually think about how you would map the output to the input. Okay, how you would know, basically whether the output would correspond to Y1 or Y2. Basically, it depends on whether you're going up or going down from the present value. Okay. Any questions?
Yeah.
Okay. We already now covered the basic characteristics of sensors. Now we're going to talk about signals, okay? And then we're going to talk about some specific examples of sensors. The signals are usually defined as the phenomena that describe the function states and their variation in a system. Okay. Basically, the signals are basically the output of sensors over time, basically. Okay. So any signal is just basically, if you're measuring pressure, for example, you might have a pressure signal. Pressure signal means that the pressure value over time. If you're measuring concentration, concentration is a chemical signal. Okay. Basically, this can also be a chemical signal, meaning that if you have the concentration over time, this is a chemical signal. So basically, the phenomena, whatever you're trying to measure, whatever the physical quantity that you're trying to measure, basically, whatever the actual measurand, the thing that quantity that you're trying to measure, basically, this is its trajectory over time is basically the signal that you're talking about. Okay. And usually such signals provide information about the states. For example, if you're talking about the temperature, if you measure the temperature for a human being, you would know that if this person is normal or abnormal. Okay, like what people do now in when you're entering a mall or something like that, you usually get your temperature measured so that you make sure that basically you are okay. So basically, this can provide information about the state, how well you are, or how your state is, basically. But actually gives them some information also about the process dynamics. If you think about a signal like the ECG, like the electrocardiogram, okay, basically the electrocardiography basically represents the electrical activity in the heart. Okay, if you measure that, you can actually know what's going on in the heart, and you can actually diagnose some conditions, some heart conditions based on that. So the signal not only tells you where you are, it tells you what's going on also. Okay. In order for you to analyze the signal, you have to know exactly the generation locus, and basically the generation locus means the spatial and temporal correlation, meaning that if you take a measurement from somewhere, it's different from another. Okay. For example, sometimes if you want to measure your temperature, you can measure your temperature from the forehead, or you can use a regular thermometer, basically that you can use it inside the mouth. Okay. They basically measure two different temperatures, but you can relate them together. Okay, so basically, if you are 37 degrees from the thermometer that is placed inside the mouth, you're okay. If you are 37 degrees from the forehead, actually you are a little bit, warm. Okay, because usually the forehead is cooler than the inside of the mouth. Okay, so basically it depends on the spatial and temporal correlation. Where exactly you took the measurement and when. Okay, there are so many examples about that. So basically you have to know exactly where you got the measurement from and when you got the measurement. For the special case of biosignals, you're actually acquiring the signals that you have, or acquiring the quantities or measuring the quantities from living organisms. Okay, so biosignals are by definition those signals that are acquired from living organisms, organs, and organ parts down to single cells. So basically, anything that you acquire from a living tissue or something like that, this would be a biosignal. Okay, they can still be electrical, mechanical, chemical, but actually they are called biosignals because basically they are coming from a biological signal, biological source. Okay, there are so many types of signals. The most important are the electric and magnetic signals. Usually you combine electric and magnetic because usually what you're measuring is something like an electromagnetic wave. And basically if you have electricity, you will have magnetism associated with it. If you have a current flowing in a wire, for example, you will have magnetic field corresponding to it. If you have a magnetic field changes, you will actually induce EMF in a wire. So basically they are related. So basically consider them electromagnetic signals or electric and magnetic signals. They are very similar to each other. If you have acoustic signal, like for example, the sound intensity, like speech, okay, this is acoustic signal, okay. There are chemical signals like the composition of a substance, like the concentration, things of that sort. These are chemical signals. You have mechanical signals like the size, the shape, the displacement, the acceleration, the flow, things of that sort. So for example, if you're talking about the measurement of the speed of your car, this would be basically, you're talking about the speed, basically. You can measure also the acceleration. You can measure the displacement, how far you went, for example, okay? And if you're talking about, if you have a water meter or something like that, then you're talking about the flow. How much water flew in 1 minute or something like that, basically. You heard about the new smart water meters. Actually, they are good examples of that. Basically, they are measuring a mechanical quantity, which is the water flow. Optical signals, there are optical signals like color, like luminescence like when you have something like phosphorus, okay? Phosphorus, basically, if you basically you have something made out of phosphorus, and basically you took it in a dark place, you will see that it basically produces light in the dark without any electricity inside or something like that. Basically, it's a phenomenon, a natural phenomenon. This is actually an optical signal. And basic color is an optical signal also. So basically, if you're using a camera, then you're actually collecting an optical signal. You might have also thermal signals like the temperature, which is the simplest one, okay? So basically we have so many of these. Let's try to basically take examples of these and basically look at the sensors that basically we are using. If you want to take some examples about the biosignals, I'm sorry, because actually my examples are usually biomedical, but they are usually very intuitive. We all know biomedical signals usually. Biosignals usually are very common than, much more common than the others. So basically, if I talk about heart sounds, okay? Like basically what the doctor hears in the stethoscope. سماعة الطبيب. لما الطبيب بيحط السماعة بيسمع إيه؟ بيسمع heart sounds. Okay? So basically, if we go back, which one of these types would you put the heart sounds?
Acoustic.
Acoustic, right. It's acoustic signal because basically it's sound. How about the heart electrical activity? The ECG. Which one of them would correspond to an ECG? The ECG is basically what you have when you measure the electrical activity of the heart. Basically, it's going to be electrical and magnetic. So basically, the same organ inside the body can actually have more than one type of signals, actually. And actually, for the heart in particular, which is really the most efficient pump that you can see anywhere in the universe, probably, you will have also flow. You will have blood flow. One of the very important signals that people use to diagnose heart condition is what's called the cardiac output. Okay, basically the electrical activity of the heart basically correspond to the signal that you're using to basically excite the pump, which is the heart. Okay, the heart itself is a mechanical pump. Okay, you're exciting, or basically the input to this pump or the signal that basically operates this pump is the ECG. But the actual work that it does is mechanical, is basically pumping of the heart, pumping of the blood to the whole body, basically. So basically, if you measure the amount of blood that the heart produces every minute, it will be the cardiac output, and basically this will be a mechanical signal. Okay? So this is very important. Okay? There are other, basically you have body temperature, which is a thermal signal. You have, for example, blood flow velocity in one of the arteries. This is, of course, a mechanical signal. You have pressure. Blood pressure also is a mechanical signal. Okay, I told you about the cardiac output, which is the amount of blood that is pumped from the heart every minute. This is also a cardiac, basically a mechanical signal. If you look at, for example, the oxygen saturation, for example, this is very important. The concentration of oxygen, or basically the ratio between oxygen and carbon dioxide in the blood. Okay, this is definitely a chemical signal. Okay, because actually it has to do with concentration of oxygen and carbon dioxide. You have a similar chemical signal in the respiration, basically the air coming out of the patient or the subject, basically. The concentration of oxygen and CO2 are also chemical signals, okay? So you have all kinds of signals inside the human body, but actually you have to consider some other examples for non-biomedical signals related. So let's start first of all, yes.
What about radiation? Is it considered as chemical or electromagnetic?
Radiation itself, it depends on what you're trying to do with it. But actually, you can actually have it as a separate type if you want, because radiation itself, it's an electromagnetic wave. When you have an electromagnetic wave, you can actually measure it as basically an electrical magnetic signal. Okay, so basically you can measure it this way. If you have a radiation based on particles, particles can be detected by their mechanical impact on some transducers, and this can be actually mechanical. Okay, so it depends on the kind of radiation. Of course, you know that the radiation can be like alpha and beta. Alpha and beta are basically particles. Radiation, you know, looks like particles, like particles basically moving at very high speed, and beta is basically just electrons, basically. And basically, they are moving at very high speed, and basically can destroy the human cells by just destroying the DNA, basically, inside. You have also gamma radiation. Gamma radiation is just electromagnetic waves. Okay, so basically, if you have gamma radiation, it's going to be just basically one of these sensors actually can actually detect gamma radiation, basically. Okay, but sometimes you do something like you detect its effect on some chemicals or something like that. You can actually get basically a chemical effect out of it. So it depends on how you look at the radiation itself. Okay, but you can basically, you can generally consider it as a different category from the other ones, but actually you can usually relate it to the other ones. So basically the first type of signals, and basically we're going to talk about the signals and the transducers that are used for it. First of all, the electric and magnetic, okay? If you ever try to get a signal from a human being, basically you use a transducer that looks like this. Basically, they are just metallic contact that is basically placed on the surface of the skin. These are called external transducers or external electrodes. You can actually have these as disposable electrodes that, like, you can put them on the chest, and basically you have adhesive, and you basically connect to the skin by a certain conductive gel or something like that. Or you can have something that looks like this. This is basically like a suction ball here. You basically press it, and basically this is made out of rubber. Okay, so basically you press it and basically place this cup here on the skin and leave it. So basically it sucks air from the skin. So basically it gets connected to the skin just by suction. Okay, these are called suction electrodes. In essence, it's just a metal in contact with the skin. Sometimes you have sensors that are just basically like needle. Okay, needle means that it's just like a needle. Just, basically you place it in the location where you need to get the signal. Okay. You can actually consider these very similar when you have a voltmeter in the lab. You basically have basically probes, right? Use probes like the probes that we use in the oscilloscope, for example. Okay, you can consider these as transducers because basically they are sensing electrical signal and basically conducting these electrical signals to the device where you measure them. Okay, these for electrical signals are very easy to measure basically. For magnetic signals, you can put something that looks like this. I think most of you didn't take 302, right? EE302. Have you taken 302?
No, not yet.
Okay, so basically this is from physics. Basically, if you have a loop, just a loop, a metallic loop like this, okay? And basically you have a magnetic field going through that loop. If there are any variations in the magnetic field, there will be an EMF basically generated inside the loop itself, okay? And you can basically use that current to basically, if you measure that current, you will be measuring the magnetic field because they are related, okay? There are some newer sensors that look like this. Actually, they called squid sensors. They are very advanced, actually. They use some new techniques, actually, in order for you to be able to measure magnetic field. But actually, let's forget about them. Just consider a magnetic field that can be measured through an antenna somewhere, okay? If you just put a conductor in the magnetic field, and the magnetic field, whenever the magnetic field changes, you will be able to get a current that corresponds to the changes in the magnetic field. Okay, so this can be very easy to measure actually. Okay, but eventually both of them actually will produce an electrical signal. So basically whatever you're measuring here from this sensor or from this loop right there will be an electrical signal in the form of a voltage. Okay, here it's exactly the same. Let's go to the more, I don't want to say, maybe you haven't heard about many mechanical sensors before, but actually mechanical sensors are really important. You have so many applications. So there are actually in idea, in principle, actually they are also very easy. They are based on basically some electrical quantities, but actually the changes in the electrical quantities have to be actually related to a mechanical change. For example, if you have a sensor that looks like this is an actual sensor actually. It basically, it's just a resistance. Basically you have a wire like this. Basically, if you have a BCB, if you have a device that looks like this, or a non-conductive surface that looks like this, it's usually made from a flexible material. But actually, what you see here is a conductive, basically coil. Basically, it looks like a coil like this, basically. Okay, and basically this is allowed to change in one direction. Basically, if you have basically whenever it has the its normal state, actually it has a certain resistance. When you have tension, when you actually pull it from its sides, what will happen is that the lines that you see here will be narrower, because when you basically consider that you're basically applying tension to a flexible cord or something like that. Okay, what's going to happen is that when you basically have a strain meaning that the length in this direction would be more. So basically you have exactly the same material here. The material here didn't change. If you actually increase the length, the width has to be reduced by the same ratio, so that the same quantity of material will remain the same. So basically, whenever you have tension, what's going to happen is that the length will be more, the area would be less, the surface area here, the thickness of this will be less, and so the resistance will increase. You're basically increasing, you have rho L over A, if you remember from the resistance, rho L over A, you have L increased and A decreased. So basically, both of them actually increase R. If you have the opposite situation, when you have basically compression, this means that the length will be less. Whenever the length is less, the area is more. So basically here you have smaller A, we have larger A, and you have a smaller L, and this reduces, both of them actually reduce R. So basically you can have resistive strain gauges that actually measure that, or you can have sometimes capacitive strain gauges. So basically you can create these as capacitors actually, but they are not as efficient as the resistors, by the way. Whenever you have something that looks like this, whenever you change the dimensions, what's going to happen here is the distance between, or the separation between these plates will be different. Whenever you have different separation, you will end up having a different capacitance between these sets of plates, okay? So basically here, you're trying to measure the same quantities here, the same quantity, the same strain that you were measuring here with the resistance, you're trying to measure that with a capacitance. It's there, it's basically there are some components that are based on capacitive strain gauges, but actually the most commonly used is a resistance strain gauge. There are other types that measure, for example, position, okay? The simplest of these is basically just a potentiometer, okay? If you have a potentiometer, or potentiometer can look like this or like this. When it looks like this, we call it a slider, okay? And basically, when you change the position here, basically it changes the position where you take the middle part of your resistance. Basically, the potential division basically on the resistance will be different, because you're basically separating the resistance in different ratios. So basically, if you couple this to a mechanical quantity. Here you actually measure rotation. Here you're measuring translation. You basically, when you do that, you're basically converting this mechanical motion, mechanical rotation here into voltage, and you're basically doing exactly the same thing here when you're moving in a linear fashion. So basically the rotation here will change the resistance, and you can actually change or make the resistance changes correspond to certain voltage so that you can actually measure it as an electrical quantity. Here it's exactly the same. Okay, so you can use potentiometers, whether they are rotary or potentiometers like this, or sliders where actually you can move in a linear fashion like this to measure a mechanical motion. Okay, this actually we do every day basically. Whenever you have like for example, if you have a volume knob or something like that, basically it takes the mechanical motion from your hand and basically determines where the position of the knob is, and basically changes that to electricity and basically uses that to whatever application you want. Okay, so basically this is the simplest form of position sensing. If you want to measure something a little bit more sophisticated, like if you want to measure pressure, or if you want to measure pressure, or actually sometimes you can actually do that with a position also. Basically the piezoelectric effect is basically converting pressure into electricity. Pressure, by the way, is a mechanical quantity. So this is still an example of mechanical sensors or mechanical measuring mechanical signals. Okay, because pressure is a mechanical signal. So basically the piezoelectric effect is the production of electricity by pressure. Okay, whenever you put a pressure on a piezoelectric material, you will have a voltage coming out of it. The reason behind that is that basically the piezoelectric materials are usually made up of silicon oxide. Okay, whenever you have a silicon oxide or quartz, this is quartz basically. Okay, silicon oxide is basically quartz. Whenever you have a quartz signal, its crystal structure looks like this. Okay, whenever it's unstressed, if you look at these sides, both sides of from between here and there, you have a silicon here, you have a silicon here, and you have O2 here. Okay, you have one positive, and two negative here. So basically you have exactly, but actually silicon is the second. Basically, you have two of these that offset the other ones from this. So you have two positive and two negative, and basically when you have that, you have neutral side from here, and here is going to be exactly the opposite. You have one silicon here, and you have two O2 here. Basically, if you look at that, basically it's going to be almost neutral as well. So basically, you can consider it as this. Basically, you have two positive here, but actually they are the two negative here. I'm sorry, will basically will be offset by the positives from here. You have the silicon here, and you have the silicon here, and basically when you have that, this will have negative voltage, and the positive voltage from these two will be offset here. You have two positives and one negative. Here you have two negatives and one positive, but the positive is closer to the surface here. So the end effect will have, when you have a strong positive and weak negative, but multiplied by 2, they will be offset here. So you'll have neutral here and not neutral here. In order for you to understand what's going to happen, or how the potential actually is increased, basically whenever you have a compression, what happens is that you're forcing the negative values or the negative ions inside. And basically this brings in the positive ions outside. So basically, in this case, if you compare this case to this case, the distance between the positives here to the surface will be less, meaning that the total here would be more positive. On the other side, when you push that here, you're bringing in the negatives from here and there and pushing back the positive from here. So basically here is going to be more negative. The opposite happens when you do basically an extension, or basically you're trying to basically pull the two sides basically outside. This will have the negative will be close, and the positive will be pushed back, okay? Meaning that the distance from the surface here will be more, meaning that the total here will not be exactly equal like here. You will have more negative here. On the other side, you have the positive here close, and the two negatives will actually be pushed back. So basically, the total here will be more positive than with this situation here, okay? In this case, you will end up with a charge that corresponds to the delta F, basically the delta of the pressure, or basic delta F is the force basically applied. And basically, if it has a certain area, basically this corresponds to the pressure. So you have a change in the charges of this device, or this sensor, depending on the kind of pressure that you applied on the sensor. And basically, because actually the quartz is not a conductor, it means that when you have the charges on both sides of the crystal, they will act as a capacitor. When you have a charge on a capacitor, this will correspond to a voltage. And basically, this is what we measure. So basically, whenever we measure a voltage on a piezoelectric transducer, we are measuring the charges that were actually the charges that actually resulted from either the pressure or the extension of the crystal itself. Okay, so basically here, the voltage will correspond exactly to the pressure. Will be proportional to the pressure here. It's going to be proportional to the Q, the delta Q, basically the charges on the surfaces of the transducer, and basically this will be corresponding to the delta F, the force changes, and basically given that the area is constant, basically the change in force will correspond to the change in pressure. Okay, so basically for the piezoelectric transducer, basically you're converting pressure into electricity. The interesting thing about the piezoelectric effect is that it's actually, it goes two ways. It's actually reversible, meaning that if you actually apply an electric voltage on a piezoelectric material, it will convert it to pressure. And this is actually what is used in several applications, okay? Let me give you some of the most common applications. Some of you actually use that. How many of you use the sensor like this for Arduino? Have you used a sensor like this for Arduino? This is like a what do you call it? Distance measurement.
Yes.
Okay, let me tell you about the example here. And basically next time, inshallah, I'm going to start with this application again. Basically, we all know about the parking sensors, right? Parking sensors look like this. You all saw that, right?
Yes.
You know how parking sensors work?
Basically, sonic wave.
Basically, yes. Parking sensors are piezoelectric materials, okay? Basically, if you go back here, instead of actually measuring the pressure here, what we're measuring, actually, we're going to measure the pressure also, but actually, in order for us to produce a wave, we have to actually put a voltage here so that we can create a pressure wave. Pressure wave is sound, basically. If you move a surface very quickly, you can actually produce a sound wave. But actually, for the application of parking sensors, it doesn't make sense for you to produce a sound wave because actually it's going to be really noisy. So what people use is usually an ultrasound wave in the range of about 100K or 80K hertz. Basically, our limit of hearing is about 20. So basically, if you use any frequency higher than that, it will not be audible. So basically, what happens is that you will have sensors like this, exactly like this, and basically you send to them a certain pulse, like a voltage pulse. When you send a voltage pulse to a sensor like this, it will convert it to an ultrasound wave. The ultrasound wave will be produced basically and goes basically until it faces an obstacle and basically gets reflected back. You actually use the same exact sensor, okay? After you send the pulse, you start listening, okay? Whenever you get the reflected wave, you can actually measure the time between sending and receiving, and basically knowing the speed of ultrasound, you can actually determine the distance between the parking sensor and the obstacle, okay? The speed of sound, by the way, is about 340 meters per second in air. So basically, it's kind of slow. If you compare it to the speed of light is 300,000 kilometers per second. Okay, compare 300,000 kilometers per second to 340 meters per second. Okay, it's much slower. Okay, so basically, if you're trying to use something like this, for example, some cars actually have very advanced features like what they call it blind spot detection, okay, or blind spot protection, okay. They actually can detect cars around them while they are moving at a high speed. If you're using ultrasound will be very slow, okay. By the time you get your signal, the other car might actually be gone already, okay. So basically, it depends on the application. You can use basically ultrasound or other techniques like electromagnetic waves. Piezoelectric transducers are used in sensors like this. This is actually an actual Arduino sensor. In this particular sensor, it actually produces ultrasound from one sensor and detects by the other. So basically, if you put these in front of an obstacle, you will actually be able to measure how far the obstacle will be. Okay. It's used also in medical ultrasound. Medical ultrasound uses probes that looks exactly like this. All these are arrays of piezoelectric materials. Okay, so basically you can actually use them to basically produce ultrasound and basically send it through the human body and basically get the reflected echoes back and build an ultrasound image based on that. So basically, a very simple transducer like this has so many applications, so many very important applications actually. Okay, so one very important caution about piezoelectric materials is that basically, as I told you, one of the piezoelectric material can be made out of quartz. Right? Quartz have a certain crystal structure that looks like this. If you actually take one piezoelectric transducer and heat it up, okay, you're going to be destroying the crystal structure, meaning that the transducer will no longer work as a piezoelectric transducer any longer. Okay, so sometimes when people use, for example, for the medical sensors like this, basically, sometimes after you use it on a patient, you need to disinfect it before you actually use it on another patient. In tools like surgical tools or things like that, you just place them somewhere where they can actually raise the temperature and use overheated steam, things of that sort at high pressure, so that they can actually make sure that all the microbes are basically removed. For ultrasonic transducers, if you do that, this will be basically the destruction of the transducer. If you actually put it in a sterilizer or in a basically heat oven or something like that, the transducer will be basically destroyed. An ultrasonic transducer can be as expensive as 100,000 reals. Okay, so if you happen to work as a biomedical engineer somewhere, don't get any ideas about trying to disinfect an ultrasonic sensor or ultrasonic probe using heat, okay? Because it would completely destroy the piezoelectricity inside the sensor, okay? Next time, inshallah, I'm gonna start with this again because this is very important, okay? So basically, I'm gonna start with the piezoelectric transducer again, but let me now go back to what we talked about at the beginning of the lecture, just the few issues that I wanted to bring to your attention. Basically, I wanted to let you know that the simulation experiments are not due anymore. They have been canceled. Please submit your lab reports if you haven't done so already. For those of you who took the lab, I think I remember two of you already talked to me about basically transferring their lab grades from the previous section of EE306. Some of you actually took the 306 in the last summer, and basically, unfortunately, they failed the course. Basically they got an IC, and then next term they actually didn't talk to the instructor. So basically, it was converted to automatic F. So basically, they wanted to just transfer the lab grades and the project grades into this section. we can do that, but please remind me again, because I don't want to miss anyone or basically forget about any of you, okay? We need to schedule 3 exams. We need to schedule very short exams for the lab and the project, and we need to schedule these actually next week, sometime next week, maybe by the end of next week, and we need to schedule a 2-hour final exam during the week after, okay? So in 2 weeks, okay? After 2 weeks, okay? So please try to arrange for suitable times. If you can't arrange that, I'll suggest dates, and if somebody has a problem, he can let me know. I want to do that because I don't want you to get, you know, you don't want to have so many exams, like exams in one day or exams in consecutive days, because we don't have much time left in this term, actually. That the exams will be crammed in only 1 week, basically. And basically, it can be a problem because they can actually be, basically, if you're taking several courses during one day, the instruction we got is that the usual is that you schedule your exam during the same time as your lecture. So basically, you might have several exams during the same day. So what I wanted to do is basically move our exams much earlier than any of the other exams so that you can actually space out your exams and don't have any problems studying for them. One very important thing is that the last day to submit any assignments, if you have any missing assignments, like the homework, like the project, like the lab reports, the deadline, the absolute deadline will be April 16th. Okay, please abide by this deadline, okay? We cannot give IC grades unless you have a very strong reason or a very compelling circumstances. And basically, in this case, we have to convince the department that actually they are basically a good reason to give an IC, to get an IC. So please don't ask me for IC grades. Ask the department, okay? The department chairman, Dr. Ajur, which is the assistant of the chairman for regarding the undergraduate. Basically, if you get their approval, I'm fine, okay? I don't have any problem. But actually, I'm not authorized to basically look at the circumstances myself. So basically, there is a general policy for the whole department. You have to actually go through them, okay? If you have any questions, let me know. Inshallah, everything will be okay. Inshallah, by the end of this week, we will be done with the theoretical part. I will send you the list of contents for the exam, and it will be much less, or at least it's going to be like much more focused than the comprehensive content that we already took in the course, okay? Any questions? Any questions? Okay, so if there are no questions, inshallah, I'll see you on Thursday, bismillah. Okay, starting next week, we'll have only 2 lectures on Sunday and Tuesday. Okay, like we did before. We already took several additional lectures to catch up or to basically try to finish early. And starting from next week, all the lectures will be just answering questions. If you want me to explain anything again, I will be happy to do that. If there are any parts of the course that we didn't get from the lectures or you have problems with, I can re-explain them again, okay? So starting from next week, you're on the driver's seat, basically. You tell me what to do in the lecture. Or if you have any questions, or if you have any issues you have in the project and any homework, I can actually help you with that, okay?
Thank you, Dixon.
Okay. So I'll see you on Thursday, inshallah. Assalamu alaikum.
Salam.